Thanks, Mike. Thanks very much to the organizers for putting together this really stimulating school and for inviting me. Over the next 2 or 3 days, I actually want to tell you about a topic that's very new to me. It's something that I'm still learning about, so I'm not really an expert, but I've had a lot of fun thinking about this area. So I hope to share some of these insights with you. And the general theme will be to think about some recent developments in error correction, namely the construction of so-called good LDPC codes. I'll explain what those are from a more physics, through a physics lens. Okay, so I'll start with some slides and then I'll switch to the board. Okay, so a theme that most people working in ultra-quantum matter are very familiar with is that there's a deep connection between the study of error-correcting codes on one hand and the study of ordered phases of matter in condensed matter physics on the other. In particular, models of error-correcting codes, so-called stabilizer codes, are associated with commuting projector Hamiltonians. And these models also end up being zero correlation length fixed points of non-trivial phases of matter. Okay, and these are usually solvable fixed points of these phases. And the intuition is that when you want to build an error-correcting code, you want a way to be able to encode information, whether classical information or quantum information, in a robust and redundant way, okay? In a way that's going to be robust against various noise that might be present in some physical realization that's trying to corrupt the information that you might be trying to transmit or process, okay? And one way to robustly and redundantly encode information is by encoding it in a particular way in macroscopically distinct degenerate ground states of some many-body Hamiltonian, okay? When you have degenerate ground states, this forms what's known as a code space. The set of ground states will form the set of states that you can encode into. And the fact that these are macroscopically distinct, the fact that they look very, very different from each other, will make the information that's encoded robust to local errors. Okay, and again, we'll discuss examples of all of this. So then you might ask, okay, how do such macroscopically distinct degenerate ground states arise? And well, they arise due to the presence of many-body order. In particular, you could have spontaneous symmetry breaking order, just conventional spontaneous symmetry breaking order. And those are generally associated with classical codes. Or if you have topological order, then that can be associated with quantum codes. Okay, and as people in the IAS formulated, these are actually more closely related than you might think, because topological order can also be understood as a type of spontaneous symmetry breaking, but of what's known as a higher form symmetry. Okay, don't worry if you don't know what that is, but the main point I want to get across here is that error correcting codes and ordered phases of matter go hand in hand. Okay, so as some examples, okay, the most well-studied canonical example of a quantum error-correcting code is Kitaya's 2D toric code. If you're not familiar with this, I'll explain it briefly towards the end of this lecture. And this 2D toric code is also simultaneously a very well-studied model of topological order. Okay? And it's in fact precisely the topological order which makes the system locally indistinguishable, and that same property goes hand in hand with a robustness to local errors. Okay? Much of ultra-quantum matter has been inspired by the study of so-called fracton phases of matter. Okay? And these, of course, came about, again, from the study of a new type of error-correcting code, Haas code in 3 dimensions, which ended up giving an interesting new phase of matter, which has been very well studied by various people in this room. Okay? But even without thinking about such exotic examples, as I was mentioning, just good old spontaneous symmetry breaking, if you just have what's known as a repetition code, okay, that's just saying you want to protect one bit of information and you just repeat it many, 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 many times. Okay, if you repeated it many times, then if there's some bit flips that are happening, you can recover the information because it's been repeated many times. That's a repetition code. But these two if you just have one bit, which is up or down, and you repeat it many times, this all up and all down, these two states, can also be viewed, or are the states of a 2D Ising model, right? Where what I've drawn here is just an Ising interaction term. So when you have spontaneous symmetry breaking, such as in the Ising model, so that you have two degenerate ground states related by symmetry breaking, then this also helps you encode classical information, okay? And something that I'll mention over the course of my lectures is that there's actually a deep relationship between quantum codes and classical codes. So some of you might be familiar that the 2D toric code, which is a particular point in a Z2 gauge theory, can be obtained by starting with a 2D Ising model or repetition code and gauging it. Okay, so there's a way to go between classical and quantum codes through this gauging map or gauging relationship, and that's another kind of theme that's very prevalent in the study of error correcting codes and phases of matter, and I'll discuss what that means for these new families of codes that I want to talk about. Okay, so what's going to be the theme of these lectures? So they're going to be grounded by various recent breakthroughs in error correction. And in particular, two breakthroughs that I want to mention is that so-called good quantum LDPC codes have been constructed. Okay, so good is actually a technical term here. It means something. And this good refers to a class of codes which optimize certain trade-offs between the density of information that you can encode and how robust it is. Okay, this density of information is captured by something called the rate of the code, and its robustness is captured by something called the distance of the code, and I'll define these for you. Okay, so after many, many years of searching, just in the last 2 years, so-called good quantum LDPC codes were finally constructed. On the classical side, there was also a breakthrough. We already had good classical LDPC codes for many years, but good classical LDPC codes which also satisfy a property called local testability. So these are codes which are not only very robust and have a large information rate, but which can also be checked very, very nicely, have some properties which allow it to be checked very efficiently. These were, again, a big open question whether these exist, and these were constructed, again, in the last couple of years, using very similar constructions as the ones that were used for good quantum LDPC codes. Okay, so these were two breakthroughs in error correction, which have spurred a lot of work in computer science and math and in various such areas. But both results for their construction required codes to be defined on non-Euclidean expander graphs. Okay, so on the previous slide, when I was talking about the toric code or the Ha code or the repetition code, these were all codes that were associated with conventional lattice models and local conventional lattice models. But these new families of codes, they're going to be defined on these more abstract geometries, and in particular, these non-Euclidean expanding geometries. Okay, so you should think of these codes as living on graphs, and that families of graphs that are going to be of interest I'll mention what those, I'll define what those are in a lot of detail later in this lecture. Okay, but when you think about an expander graph, what you should visualize is a picture that looks something like this. Okay, and this is something which is locally tree-like. Okay, you start at some node and then you're branching off. But what those fuzzy lines at the edge are supposed to denote is that the whole graph is connected up in some way, so that every vertex is actually just the same as any other vertex, statistically at least. Okay, so there's no actual root and there's no actual boundary. And what the expansion refers to is that these types of graphs, these expanding graphs, have a very, very strong surface to volume ratio. And in particular, the boundary of any subset of sites in this graph, okay, you cut out some chunk of sites, and the number of sites that neighbors that chunk is going to scale proportionally to the size, to the volume that you cut off. Okay, so surface areas and volumes scale proportionally to each other in these geometries. Okay, and that's going to lead to various interesting physical properties. So I should say that, it might seem a little bit abstract. People again, in computer science and optimization theory, there's a long history of studying statistical mechanics models defined on graphs. But, there's also such types of geometries are also increasingly accessible in new types of synthetic quantum systems, okay? So traditionally, condensed matter physicists have studied lattice models because, if you want to study electrons in some crystalline solid, the solid is arranged in some periodic lattice, or the atoms in the solid form some kind of periodic lattice. But now, you have these new types of geometries which are increasingly accessible, and these platforms so here there's an image of a platform from an experiment in neutral atoms from Misha Lukin's group. And these are extremely tunable, okay? So you can actually pick up the atoms, bring them next to each other, cause them to interact, take them out. So by moving these atoms around in this way, you can really engineer very interesting types of, very tunable, very interesting types of effective geometries, effective interactions. And in this picture, I'm showing you atoms interacting via certain cavity modes, which can again be used to engineer various tunable types of geometries. Okay, so the study of physics on these types of geometries and graphs is not just abstract, but it's actually something that is increasingly experimentally relevant as well. Okay, so what are the key messages that I hope to convey over these 3 lectures? One is that LDPC codes, just like various other models of error correction, like the toric code or fracton codes, LDPC codes, which I'll define for you, also furnish an interesting new class of statistical mechanics models for many-body physics, and they lead to novel phenomena in non-Euclidean geometries, okay? So that's the first message. The second is that just like a lot of the framework that has been developed, again, in thinking about topological order and fracton phases, we can also understand these different LDPC codes as generalized gauge theories, okay? And we can, in fact, formulate symmetry breaking order, topological order, and SPT order on these different types of non-Euclidean graphs, and formulate generalized Kramer's one-year dualities relating these phases. Okay, so in Shu Heng's lectures, you heard a lot about Kramer's one-year dualities on models, interesting models in Euclidean lattices, and these types of transformations can also be formulated for these very general codes. Okay. Then what I want to do is to unpack. So there's lots of constructions. Again, these codes were mainly developed by mathematicians and computer scientists, and they used various constructive principles to build these codes. And what I want to do is to unpack these different constructions in the coding literature in physical terms such as symmetries, redundancies, excitations, in terms where as a very humble physicist who's not very mathematically sophisticated, I can still kind of look at those constructions and get a sense for what they're doing, okay? And a key role that will be played in doing this is a unified description of codes via homology theory, okay? So I'll show you, this is a very, very powerful framework, and actually codes in any dimension, whether it's 1D, 2D, 3D, or these infinite dimensional expander geometries, can all be understood in a very common language using this type of framework, and then you can understand what these product constructions are doing in that language, okay? And finally, if there's time, I want to tell you about some actually very recent work, that's kind of more illustrating point 1, that these are interesting StatMech models, that these codes actually furnish new types of analytically tractable models for both classical and quantum spin glasses, okay? So this I may get to in the last lecture. Okay, so the plan is now I'm gonna take away the slides, and I'm going to just describe to you what classical LDPC codes are, starting with what is a classical code, what is an LDPC code, what is a good code, and why are expander graphs necessary. Okay, so that's going to be today's lecture. And then I'm going to move on to quantum LDPC codes, and actually it'll help us to really have this deep understanding of classical codes, because what these product constructions do is they actually build up these quantum codes out of products of simpler classical codes. And a lot of the properties of these quantum codes can actually be understood just by understanding the properties of those underlying classical models. Actually, even the 2D toric code can be understood as a type of product of two 1D-izing models. Okay, and I'll explain that next lecture. So once we've understood these classical codes and we've understood these product constructions, that'll actually help us really understand various properties of these quantum LDPC codes. And then, yeah, so, and then I'll move on from there. Okay, so that's the plan. I'm now going to remove the board and switch to slides. Any questions on the general themes and the motivation for what we're trying to do? Yeah. I can't hear you, sorry. Wow, okay. Yes.
David actually answered it, but.
Oh, okay, all right. Any other questions that they didn't already answer? Is this big enough?
Yeah.
Yeah, okay. Okay. I'm going to start by describing what are called linear classical codes. Okay. And the goal is to transmit K messages. Okay. And these are often also called message or logical bits. This is the information that you want to transmit. And you're going to encode this into n greater than k physical bits. Okay, and n is greater than k because whatever the message that you want to transmit, you want to encode it redundantly so that if you have some error channel that's coming in and trying to corrupt your information, there's some room in there, there's some redundancy in how that information is encoded for you to be able to recover the message that is sent. Okay, so as an example, suppose you want to transmit k equals 1 bit of information. Okay, so k equals 1 bit. So this 1 bit can be either 0 or 1. Okay, and now the error channel can come in. Again, we're just doing classical codes here, just classical bits. So some error channel can come in. You want to send either 0 or 1, and some error channel can come in and try to flip that bit. Okay, so if you're only sending the information in one single bit, if the error channel flips it, well then it's lost with the probability with which the error channel flipped your bit. Okay. On the other hand, suppose you take this 1 bit and you repeat it many times. Okay, so let me repeat it 7 times here. Okay, so now I'm going to take this, I'm going to repeat it many times, and now I'm going to send this again over some noisy channel. Now the channel is acting with noise, so bits are getting flipped. As long as the number of bits that get flipped is less than 3, okay, which has an error probability that's suppressed relative to flipping just 1 bit. So if a bit is flipped with probability epsilon, then 3 bits are flipped with some probability roughly epsilon cubed. And as long as the number of bits that are flipped is less than 3, or equal to 3, I can just do some simple majority rule and recover that okay, with high probability either a 0 was transmitted or a 1 was transmitted. Okay, so this is this kind of redundant encoding. These two messages that we want to redundantly send are called the code words of your system. And in this simple code where I just repeated the 1 bit, this is what I was alluding to earlier. and this is called the repetition code for obvious reasons. Okay? All right. So if you now want to understand what is the redundancy that you introduce by copying this one physical bit many, many times, that is captured by something called d, which is the code distance. And this code distance is the Hamming distance is equal to the Hamming distance between your codes. Okay. So in the example above, there are only two code words, and the Hamming distance between them is n. Okay. So what that means is that if an error channel, so if the errors corrupt less than d over 2 bits, then I can distinguish my codes. So the whole game of error correction is you have some information that is acted upon by some error channel, and then you want to apply some recovery operation to be able to recover the information that was sent with some high probability. Okay, ideally, you want the probability of recovery to go to 1 as something like as you scale up n. You want some family of codes where you can scale n up so that the probability approaches 1 in the limit that n goes to infinity. Okay? So, more generally, I'll have a system of, so this is repetition code. More generally, I have n physical bits, which I can represent as xi, which is either 0 or 1. Okay? So now my configuration space is a vector space, which is identified with ft to the n, f2 just the field with 0 and 1. Okay, and my vector configurations are vectors in this n-dimensional space. Okay, and basically, if you have some configuration like that, okay, so that means this side is 1, 2, 3, 4, 5, 6. This vector space is a subset which is picking out the bits at locations 3, 4, and 6. Okay, and you can take any vector, you can associate I or a basis vector with each bit. Okay, and any configuration can be written as xii, where xi is again in 0, 1, and this labels a subset of bits that you're picking. Okay, and those could be the bits that, for instance, are flipped in your configuration. Okay, so now I've described all of this in terms of bits, but we're going to switch to physical Hamiltonians. So it's also useful to go back and forth between bits and spins. So I use sigma variables to refer to spins, and even though I just talked about classical spins, I'm going to use a notation which is going to look like Pauli operators, because later I'm going to talk about quantum codes where these are going to be Paulis. Okay, so my quantum, my classical spins here, Zi, can be +1 or -1, depending on whether my bit was 0 or 1. Okay. So now, in order to encode information, I basically want to take out a code space. Okay, so this is the subspace. And this itself is going to form another linear vector space, as I described. Okay, so this code space is the subspace of my configuration space. And this is what I'm going to identify with my code space. Okay, and this is going to be comprised of 2 to the k code words. Okay, so remember I want to send k message bits. So if you have k message bits, those can be in 2 to the k configurations. So you want to pick out a subset of 2 to the k code words out of all possible 2 to the n configurations, okay? And you're going to say that those 2 to the k configurations are your code words. Okay? Now, there's a question, how do I specify what these code words are? Okay? These code words can be specified by imposing constraints. So these are specified by imposing constraints. And these constraints are called parity checks. So that would be LDPC, that's what the P and C in LDPC stands for. It's called a parity check. And these parity checks can be, these are encoded in a matrix. So there's a matrix which is in n matrix of zeros and ones, n by n dimensional matrix. I'm going to impose n parity checks here, okay? And my code space is going to be specified by the set of vectors which satisfy all the different parity checks. Okay. So what does this mean? Let's just look at a particular parity check matrix. Again, if I'm working, let's say I have 3 checks, okay, and I have, let's say I have 7 bits. Okay. So suppose I write my parity check matrix like the following. Okay, so suppose that's my parity check matrix. What this means is that when I add on this with some vector that's in my code space, so that's a 7-dimensional configuration, I want to get zeros. Okay, so for that vector, I want none of the checks to be triggered. So in particular, my code words have to obey x1, x2, this is x3, x4, and so on. Okay, so
equals 0, right?
Equals, yes. 0, and this is all modulo 2 arithmetic. Okay, so if you just had idling interactions, for instance, you would just say x1 plus x2 is 0, which means x1 and x2 are either both 0, 0 or 1, 1. Okay, so this symbol here is the exclusive OR symbol, okay, and this is basically equal to 1 if x1 and x2 are 0, 0 or 1. Okay, so this is basically saying that look at those 4 bits and the number of ones in those 4 bits should be even, okay, and then the first constraint would be satisfied. Then look at the next constraint and pick out this other set of 4 bits, and the number of ones in the configuration and those set of 4 bits is 1, then that is 0, then that configuration is that constraint is satisfied, and so on. So all right. So in particular, what this means is that x equals 0 is always forward. Okay, and the kernel of this parity check matrix gives you a basis for forwards. Okay, what the linear refers to, okay, all of this stuff, I'm just specifying a set of linear constraints acting on this, which forms a vector space. What the linear is specifying is that if W and V are forwards, okay, then so is W plus V, where once again you add these vectors using modulo 2 addition. Okay, so from all of this, the dimension of my code space K is basically n minus the rank of this parity check matrix. Okay, because the rank of the parity check matrix is telling you the number of linearly independent constraints that you're imposing on your system. So if you have n bits and you impose that many linearly independent constraints, then the number of free degrees of freedom that you have that form your code space is k, which is n minus rank of h. Okay, so this problem should remind you of different kinds of satisfiability problems that have been studied in computer science and mathematics. But actually, these are a very simple class of satisfiability problems. These are called these XOR stat problems, where the XOR is referring to how these constraints are defined. And in particular, in this class of problems, everything is linear. Okay, the solution space is linear, unlike kind of more conventional SAT problems. Okay, so once you have some number of solutions, you can just take, so once you have this basis of forwards given by the kernel of this parity check matrix, you can combine those code words to form, you can combine the basis vectors to form all code words in your model. Okay, and then finally, D, which is the whole distance, is the minimum Hamming weight of a non-zero portal. So since we're going to be converting everything, since we're going to go from bits to Hamiltonians, you can think of each of these constraints as a term in a classical Hamiltonian. Okay, so each constraint CA, A is going from 1 to n. For every row of your parity check matrix, you get a constraint or a term in your Hamiltonian, and this term basically looks like a product of classical spins, and this product acts on all the spins for which the eighth row of the parity check matrix is 1. Okay, so the Hamiltonian that you define from the set of constraints just looks like that. Okay, it's a sum of classical terms in Hamiltonian, and just like all zero is always a full word, all up is always a ground state. So now we can understand N, K, and D using this mapping in more physical terms, where N is the number of physical bits, okay? Or in physics language, this is the system sides on which my Hamiltonian is defined. K is, again, number of logical bits, or it's log base 2 of the ground state degeneracy. Okay. And D is the coordinate, which is the number of flips between different ground states. How many spins do I need to flip to go from one ground state to another? All right, so now LDPC. I already explained to you what PC means. Those are my parity checks. What LD means, this is low density. Okay, and this is a generalized locality condition. Okay, so what low density means is that H, the parametric matrix, is sparse, or more concretely, that the number of bits that each check acts on is order log. So as you make your system figure by scaling n, the range of the interaction terms in your Hamiltonian remain finite. So this is how many ones are there in each row of the parity check matrix. And then it also means a second case, which is that each bit is acted on by finitely many checks. Okay, so this is stronger than K locality. Okay, so to define this, I'll talk about K locality, which means that every interaction is acting on K bits and K doesn't scale with n. So that's the first condition here. But the second condition tells you also that every bit is only acted upon by finite many. Okay, so that Hamiltonian, the number of checks is again, this Hamiltonian has a well-defined eccentric energy. So it's not like the SYK model, for instance. In the SYK model, that's all to all. So every bit is acted upon by a number of interaction terms that's scaling to infinity, and that's not the case. Okay? So basically, the upshot is, yeah, so that's those are some definitions. Any questions?
So
Yes.
do you require your parity check matrix?
Do I require it to have eigenvalue 0? Yeah. So all 0 is always a code word. So it will have at least one configuration which has eigenvalue 0. But now the question is how many others does it have?
Doesn't have eigenvalue 0, then the only solution will be the
Yes. That you have a unique ground state then. Yeah, that's right. So then you won't have encoded. If you just have a unique ground state, then K is 0, right? Because then log of 1 is 0. And then, yeah, so then you've not encoded anything. Yep. Yeah. It's just the number of ones that appear in the code word. Yeah. So in the Ising here, D is N. Yes.
Is the Hamming distance between any two code words equal, or?
Good. No, the Hamming distance between any two code words does not need to be equal. So in general, the code distance is the minimum Hamming distance between any two code words. But you can do a basis choice by which you can map that to just the minimum Hamming weight of any code word, which is comparing it to 0. You can pick 0 to be whatever you want, is basically the point. Yeah. Okay. Other questions? All right. Okay, so now let's look at a couple of examples which we've already alluded to. So the first, as I mentioned, is the repetition code or the Ising model. All right, so now in Hamiltonian language, this is very familiar. It's just a sum of nearest neighbor Ising interactions. You can choose your parity checks to be just nearest neighbor Ising interactions. If you do that, let's look at a 1D example. Okay, if you have a 1D chain of n bits, and suppose we have periodic boundary conditions, then the product of all of these checks, so this is Cij, so product over all nearest neighbors of Cij gives you the identity, okay, because you do Z1, Z2 times Z2, Z3 times Z3, Z4 times Z4, Z5, and then finally times Z5, Z1, okay? So if I write down all of these constraints, I'm going to write down m equals n constraints here. But I have this one linear dependency. So I have m equals n minus 1 independent constraints. So then k equals n minus 1, which is 1. Okay, so since k is 1, I have 2 ground states. And once again, my 2 ground states are all up and all down. Okay, so this is k equals 1 logical bit. And in this case, my code distance d is the same as n. Okay, because the Hamming distance to go from one to the other is n. And if you wanted to write the parity check matrix of that code, okay, the parity check matrix is just 1, 1, and then all zeros, and then 1, 1, 0, 1, 1, 0, 1, 1, 0, and so on. Okay? All right. So now let's introduce a little bit more terminology. Okay? So this is the all up state, but I want to associate it with my logical bit being up. Okay, so I'm going to introduce something called Z logical, okay, which is going to label my logical bit. And this configuration corresponds to Z logical being up, and that configuration corresponds to Z logical being down. Okay, so when you're trying to build a computer, a classical computer or a quantum computer, whatever it is, you want to do some operations on your logical bits. Okay, one operation that you might want to do is to flip the logical bit. So a logical x, okay, a logical x which flips that logical bit actually has to flip all these physical bits that make up the logical bit. Okay, so the logical XL, this is why I chose to work in like these spin language, which I'm going to now adopt some quantum notation, even though I'm talking about classical spins. If I go in and I act with the Pauli X operator, which flips all spins, then that's a logical X because I've gone from a logical state being up to a logical state being down. Okay, so this flips the logical bit. But notice what this operator is, right? This is nothing more than the Ising symmetry of this 1D Ising model Okay, this could be any dimension actually. Okay, so this repetition code defines an Ising model, and the logical X operator defines a symmetry of that Ising model. Okay, so the fact that you have multiple degenerate ground states here is a statement of spontaneous symmetry breaking in this classical code. Okay, so spontaneous symmetry breaking is the presence of degenerate. The fact that you have degeneracy means that your k is greater than 0, and macroscopically distinct. Macroscopically distinct means that D scales with N in some way. Because D is scaling with N, these are macroscopically distinct, and that's giving you the robustness. You ultimately want to tell apart your different logical states, and if you want to tell them apart, even despite corruption, you want them to look as different as they can from each other. Okay? So more generally, as I was saying, your code words actually form a vector space, and you can pick a basis for this vector space by looking at that kernel of the parity check matrix. So if you label these basis states by chi lambda, okay, so lambda is going from 1 to k. This is the basis for my code words. Okay, so each chi lambda is labeling some collection of bits that are flipped in the code word. Okay, so then you form a vector, okay, by saying, okay, those were the code words, those were the bits that were flipped in the particular code word labeled by lambda. So each of these defines a logical, this is now a logical X operator, okay, which is now a product of I element of chi lambda of this Pauli X operator, which flips the spins. So this logical X operator takes you from the 0 code word to the chi lambda code word. Okay? The other thing you can do is that for every one of these vectors, you can associate it with a dual vector. And the dual vector, let's call this zeta lambda, has the property that the dot product of zeta lambda and chi lambda prime is 1 only if lambda is the same as lambda prime. Okay? So what this means is zeta lambda is some, okay, so now let's take zeta lambda and write a z lambda operator. Okay, this is going to be a logical z operator corresponding to the logical x. Because again, now I'm switching to this quantum language. You know that Pauli x and z operators anti-commute with each other. Okay, so what I'm looking for here is logical x and z operators. The logical Hilbert space forms a vector space in its own right. So when you have Pauli operators acting on that logical space, on those logical bits, you want them to have the right algebra of Pauli operators. Okay, so I'm going to this x lambda acts like Pauli x because it's flipping you between different logical states. And a z lambda is going to act like a Pauli z, which is both going to tell you what logical state you were in. Like here, I had a z lambda being up and a z lambda being down, okay? And it's going to have the property that it's going to have the right, this is like the right anti-commutation relation between the x logical and the z logical, okay? So the z lambda is a product of I, which lives in zeta lambda of these Pauli z operators on that side, okay? And what you can do is that, so this operator is flipped by x lambda, okay? So it anti-commutes with it. So what that means is that this z lambda is an order parameter for spontaneous symmetry breaking. Okay, so when you have this code space, I just worked out the Ising example for you, where there was exactly one, K was 1, so you had a single Z2 symmetry. In general, when you have this family of Hamiltonians, you have a large symmetry group, or a potentially large symmetry group, which is Z2 to the K, okay, because every single code word defines a logical X operator, and these logical X operators, they by definition, because they're logicals, okay, they don't excite any of the checks, which means that they're symmetries of your Hamiltonian. Okay, so the Hamiltonian has this large symmetry group, and what the code space is spontaneous symmetry breaking, so a huge degeneracy, a 2 to the K-fold degeneracy corresponding to all of these symmetries being spontaneously broken. Okay, and you have these X operators which identify for you exactly what those symmetries are. Again, I'm just picking a basis for the symmetries. Once you have those symmetries in this language, you can take products of different symmetries, products of different X operators like this, and get back another symmetry for the Hamiltonian. And then you also have these Z's, which diagnose your symmetry breaking. Okay? For these classical codes, give me 1 second, there's a basis in which, so there's a basis in which this can be chosen to act on a single site I lambda. Okay, so there's a consistent way you can go through, and you can pick every Z lambda to act on a single site. So by the time you are done consistently picking your Z's, you're left with K single site bits, which you can view as your logical bits. This is called putting your code in canonical form. So you can basically think of the first K bits of the code as labeling your logical space, and then everything else is kind of padding and redundant. Okay. Yes, sorry, there were various hands. Yeah.
So if you're given a set of code words, then the parity technique is not close.
Correct.
Either is the Hamiltonian, then how do you sort of canonically choose what Hamiltonian you want?
Yeah, so you can decide. The question is like, how do you pick a parity check matrix if I give you the code words? So people do this in different ways. So there are some code formulations where just the code words are specified. This is called like specifying a generator matrix. Generator because all your code words can be generated by those. And then indeed you can pick any parity check matrix. Okay, so now, just like we could go from the parity check matrix to the code words by looking at the kernel, okay, you can just invert that and go from the generator matrix to the parity check matrix. But again, the code word you only have a basis for the code words, right? Once I look at all 2 to the K code words, that's not, like the basis is not uniquely specified, only the code spaces, right? So likewise, you have freedom in choosing your parity check matrix. So it just depends on your physical problem whether you decide to specify it by looking at the parity check matrices or by looking at the code words. And then there's going to be properties of your parity check matrices or your code words, which will tell you like, okay, can I pick a local basis for my parity checks or not? Okay, so when I want to do LDPC, we usually tend to pick the parity checks, specify those parity checks, because those should be local, and then use those to build the code space. Yeah.
When most of these parameters are from the Ising, right? So
Yeah.
this is not in the canonical form, right? Because you look at the canonical form at identities on the last few columns, right?
No, the parity check matrix is just each row tells you which bits so that's my parity check matrix.
The standard linear code construction, the canonical form of it is basically like you partition the matrix into identity matrix on the right, and then
Sure. So that I'm not doing that. Yeah.
So
yeah.
If someone hands you the canonical form, is it obvious how to? It looks like you wanted the non-canonical one in this case, right? Because it's more physics.
Yeah. So I want to stick to the. Let me stick to the physicsy ways of defining things here. You can take this, so basically what you want to do is just, if this matrix has full rank, okay, so then you will just, yeah, let me just stick to the physics way of writing these, if you don't mind. Okay, yeah, David.
When you wrote Z, did you mean a sum rather than a prime?
Here? So when I write z's, I'm doing spins, and then it's a product. And when I'm doing, when I'm referring to bits, then I'll write x, y, z's. So this is a product.
Explain that in terms of the repetition code?
Yeah, so in the repetition code, my z lambda is just a single z. It's just a single side z. So this set zeta of lambda just acts on one spin.
Oh, that's sometimes a special set.
Yes. That's a special set which has this property that it's dot product.
A different set than
Correct. So X is defining the logical set, and this is defining the set which is triggered by X. So it's basically saying it's a set whose dot product is 1 and not 0. Yeah. Yes?
So the degeneracy of those check operators, arbitrary check operators always power of twos.
Degeneracy of the check operators are powers of 2s. Yeah, because no. So the kernel has dimension k, and that defines 2 to the k code words by taking all sets of all possible sets of those. Yeah. So the kernel the dimension of the kernel, k is, I had that somewhere, n minus rank of h. That doesn't have to be a power of 2. But then the ground state degeneracy is 2 to the k. Okay. All right. Let me keep going. I'm going, well, much slower than I thought. All right. Okay, so just like I have, so this was already alluded to, just like I have a vector space of bits and a vector space of code words, I also have a vector space of checks. Okay, so this is F2 to the M. So I can label each check with a basis vector. And then if I take vectors like this, then this is labeling a collection of checks, okay? And in that language, what this parity check matrix is doing, this is, suppose I take the transpose of this, which is n to m. So this then maps collections of checks to collections of bits. Okay, so it's basically mapping between the vector spaces of checks and bits, or it's telling you in spin language, if you have a set of interactions, if you multiply out all of those interactions, which bits are still going to be left. Okay, that's all this is doing. But this way of writing is useful because a very common prescription for writing codes is called a Tanner graph. Okay. So what a Tanner graph is a bipartite graph where on one side you have your nodes of this graph are your bits, and on the other side the nodes are checks, okay? And so these are bits, these are checks, so there's n bits here, there's m checks there, and then you can associate each of these with vector spaces. So there's a vector space here, a vector space there, and then the adjacency matrix of this Tanner graph. This is my parity check matrix. Okay, so people in the coding literature often construct random codes. We'll talk about those in a moment, but that's just saying take some collection of bits, take some collection of checks, come up with a random adjacency matrix between those, or come up with some random parity check matrix, and then that defines the code for you. Okay, the LDPC condition is again that this adjacency matrix has to be sparse, but in general, there's a lot of literature on coding theory where that LD condition is not really imposed. Okay, so another canonical example whose parity check matrix is actually up there already is, which I'll come to later in my lectures, is the so-called Hamming code. Again, these can be defined for different ends, but a 743 Hamming code is again something that's a very canonically studied code in the literature. So this is 7 bits, 2 to the k, so 2 to the 4 equals 16 ground states. Okay, and there's 3 checks. The parity check matrix of that Hamming code is actually what I already wrote over there. In Hamiltonian form, this basically looks like the following Hamiltonian. Okay, so there's three rows in that parity check matrix. Those are my 3 terms in the Hamiltonian. Each row has 4 ones. So each check is a 4-body interaction. So these are like generalized Ising models. Okay, and I described this Tanner graph to you. Another pictorial representation of these codes is as a so-called hypergraph. Okay, in a hypergraph, your edges can act on more than 2 bits at a time. So for the Hamming code, basically you can write all 7 bits of the Hamming code. Okay, and then this is the first check which acts on 4 of those bits. This is the second check which acts on another 4, and then this is the third check which acts on the last 4, and then you can notice that there's 1 bit which is acted upon by all the checks. So there's 1 column there which has a 1 in all its rows there. Okay, so this is kind of a very canonically studied small code. Okay, this is just a small example. Okay, so with all of this, we've now understood the algebraic structure, right, the linear algebra of these classical linear codes. So now we're prepared to study, okay, so now let's move on and talk about what good codes are. Okay, so good is an actual, it means something. So good codes are a family of codes which, so these are by a family I mean something where you have some rule for specifying it on n bits, and then you can scale n up, right? Like, so just for the Ising model, I can define an Ising model on a lattice of size 10 or 20 or 30. So in some family of codes indexed by n, I want k and d to go proportionally to n asymptotically. Okay, so notice that this is as good as it can get. Okay, so good is a little bit of a euphemism. Okay, I mean, these are spectacular, if you will, because k can be no bigger than n. K can scale no better than n. Okay, if you have n physical bits, you can't encode more than order n logical bits. And d can again be no bigger than order n. Okay, so this scaling is as good as it can possibly be. And now, the reason that I started by talking about expander graphs is that this scaling is impossible in finite dimensional local Euclidean models. Okay, and there's a bound by Bravi, Polin, and Turhal, okay, which basically tells you that for classical codes, k times d to the 1 over d, which is d spatial dimensions, is less than equal to order n. Okay, so if you have a 1D Ising model that has k equals 1, d equals n, that actually saturates that bound. Okay, so notice how terrible the 1D Ising model is. Okay, its d is very good. Okay, the d is scaling as n, but there's only 1 logical bit that you've encoded in there. Okay, so you've packed in, you built you're an experimentalist, you've built this system to have like 50 bits. Okay, but you're only sending one relevant bit of information in that, no matter how big you scale that up. You go from 50 to 100 to 10,000, you're only transmitting 1 bit. You're just transmitting it better and better. Okay, you're just making it more and more robust. Whereas what we would want is for K and D to both scale proportionally to N. Okay. Okay, everyone's, all right, yeah, go ahead. Sorry?
What is local Euclidean model?
Local Euclidean model means that you have a low density parity check, and you can think of your checks as living on some actual Euclidean geometry. So the Ising model is an example of a low density parity check code. The toric code is an example of a low density parity check code. It just means you have some actual genuine Euclidean lattice, and the interactions of your Hamiltonian are local on that lattice. Okay? Okay, so let me derive it for you. Oh, the meaning. No. So it's just saying that, like, well, it's as good as it can be, but it's still pretty crummy, right? In the sense that, like, so this is giving you a trade-off between the density of information that you can send, which is K, and the robustness, which is D. So if you try to make K big, you make D small. Or if you try to make D big, you make K small. So in the Ising model in 1D, D has been made big. D scales with N, but then K is just 1. K is not scaling with N. Okay? And what you would want, so this is what we want. Okay? You want both. Exactly. So this is what you want, but you can't get it in any Euclidean lattice. And that's why we want to study these non-Euclidean expander models. Okay? All right. Was there a question? Okay. So since I only have 5 minutes, I guess I won't get to describe the expander codes. That'll have to wait till tomorrow. But let me just quickly sketch this proof, because I can't do that in 5 minutes. Okay. So here's the proof sketch. Okay. So this is I've drawn this in 2D, but this can be, in general, any kind of Euclidean space. I divide it up into A and 2 regions, A and B. The size of this region B is, so this is in D dimensions, which I've drawn to be 2 here, okay? The size of B is L to the D, and that scales like D, but is less than that. There's a capital D, which is the dimension, and it scales like the code distance, but it's less than the code distance, okay? Now, if 2 different ground states agree on A, okay, they must agree everywhere. This is by definition, okay? Because you know that, like, the code distance is little d here. That's the minimum size of the region on which your code words have to differ. So if this box B is smaller than D, and 2 configurations which I promised you are both code words agree everywhere on A, well, then they cannot differ on B. They have to be the same, okay? Now, let me put 2 B boxes, B1 and B2, both of which satisfy this property. But because my code is local, okay, I'll say that each check, which is geometrically local, overlaps with at most 1 B block. Okay? So now this means that, okay, even though 2B together might be bigger than D, because these are totally disconnected, this property still holds, okay? If 2 ground states agree on A, they have to agree everywhere, okay? Because some problem that's happening here cannot be fixed by this block that's far away, because there's no overlapping checks between those blocks. So now, using this type of reasoning, I can actually tile my entire system with these B blocks of these different sizes. And I say that the rate of my code, K over N, this is called the code rate, okay, by the way, this K over N has to be less than the size of A divided by N, because I can only choose things independently in A to specify my code words. Once I've done that, I know that I'm done. If they agree on A, they have to be the same code word, okay? So, but the size of A here divided by the total size, okay, is basically going to be the size of the boundaries of B divided by the sizes of the boxes of B, which is going to go like 1 over L, which in turn is 1 over D to the 1 over capital D, okay? And this is where my Bravi-Poulin-Turhal bound comes from. But the intuitive picture that's happening here is that you have a ratio here, which is basically a surface to volume ratio. So you're trying to construct your code space by dividing your full configuration space into smaller blocks and seeing how that tiling is going to happen. And this is an idea that actually comes up over and over again when we're studying these types of codes, okay, which is you're trying to build up properties by tiling different boxes of different sizes. And the property that you cares about some type of surface to volume ratio. And in any Euclidean space, the surface scales not proportionally to the volume, right? But on these expander graphs, the key property that they'll have is that the surface to volume ratio is going to 1. And because of that, you can get around these types of bounds which care about surface to volume ratio and define good codes in which both K and D are proportional to N. Okay. Other questions? Yeah.
Good LDPC code,
Yes.
expander graph.
Yes.
Is the associated lattice model physically local? Because it doesn't seem that there is a notion of dimensionality.
Good. So it's going to be physically local on a graph. So actually, if you can pull the screen down, I'll just show you the picture, and then we can talk about it next time. Okay. So these are some examples of geometries or graphs. Okay. And so the graph itself has an expansion property where the bulk and boundary scaling is going to be proportional. And now I want to define codes on this graph, and the codes are going to look local on these graphs. Okay, so this is an expander graph. I'll describe how you get graphs like this next time. But then you can go in and you can decorate. You can just treat the graph like a lattice, and you can make your model local on that lattice. So I can put bits on all the edges of that graph. And on every vertex, I can put in a multi-body check, which acts on all the bits that are coming in and meeting at that vertex. And in fact, we already talked about this Hamming code. Okay, something you can do is this is a degree 7 graph. Okay, so you take this one vertex here, and if you zoom into the vertex and you look at the 7 bits surrounding that vertex, you say that, okay, the 743 Hamming code that we just discussed, you can put in 3 checks on every vertex, and those 3 checks are going to be exactly those 4 body checks that we wrote, but now they act locally on every vertex, just like an Ising interaction would act locally, wherever an edge exists on an Ising lattice. So you can kind of build up a code with an underlying lattice and a small code in this way. So this is for this kind of tree-like graph that I drew on this side. You can also look at hyperbolic tessellations of different manifolds, okay? And that can also give you an underlying expander graph. So this is what's known as a 7-3 tessellation. 3 because you use triangles to tessellate hyperbolic space, and 7 because it has degree 7. And now you again take this degree 7 interaction here, and you zoom into it, and it looks like that. Okay. Second, I'll explain next time how you construct these types of graphs and these types of decorations, and why that allows you to get a good code. Okay. Other questions? Yeah.
Can we define similar parity check codes for antiferromagnetic conditions?
Yeah, so now you're taking it a step further and just saying, okay, let me just do physics on these models. Okay, and now I can talk about antiferromagnetism, frustration, all of that stuff. So you can certainly do that, but then it'll likely lose some of the nice solvable, the nice properties that it has, but it's certainly interesting to ask those types of questions about what you can, about how to start like now having richer models on these types of geometries. Yeah. Yeah.
Can you define this code for other degrees of freedom rather than bits?
Well, we're going to do qubits. And oh no, but yes, you can also, you don't have to do F2. You can pick any, you can pick any linear space, you can pick any kind of field that you want, and then you have these general codes over some other field, and the same kind of linear algebra structure will go through. Yeah. Yeah. I don't know. Yeah.
That these graphs are locally tree-like, but they're actually not trees. So what is happening at the edges?
Yeah, so you should think of it as like some kind of like periodic boundary conditions, but it's really like the number of degrees of freedom that are at those edges is basically the same as the number in the bulk, and now all of them are getting connected up in some way. Okay, and you can do that connection either randomly, that defines a random regular graph, or there are actually like non-random ways of constructing these types of expander graphs, either by looking at the Cayley graph of some special groups, or by doing these hyperbolic tessellations. And when you do it that way, then everything that's happening on the edges is also kind of very well defined. Everything is very regular. Yeah. All right. Okay. Thanks.